This lesson will ask you to think about acid strengths measured by Ka. This is acetic acid, has a Ka. This is water, has a much, much smaller Ka. Water is much less likely to be dissociated. The type of bond broken is the same in each case. It's this OH bond. The proton comes off. This is the dissociated form of acetic acid. This is the dissociated form of water. Why is this so much more likely to dissociate than is water? Part of the answer will lie in electronegativity. You have this oxygen here, which is drawing electrons away from this carbon. But part of the answer lies in a phenomenon called resonance, where we look at what's left over. How stable is this anion? How stable is the negative ion? Resonance is something that occurs in molecules that have double bonds, particularly when you have a double bond adjacent to a formal negatively charged oxygen. It's sometimes written as a double arrow, suggesting that the two forms can interconvert. In reality, it's more complicated than that, but this is a good beginner's guide to resonance. So here I have two forms of carboxylic acid, the black one and the red one. And these are called resonance structures. They can readily interconvert. So I'm going to act this out for you. I'll be the black version first. Double bond on this side, negative charge on this side. Switch! Now I'm the red version, double bond on this side, negative charge on this side. Switch, 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 switch. So this is a way of looking at resonance. The two forms are, as you can see, readily interconvertible. Since the double bond can be in two places and the negative charge can be in two places, you sometimes see resonance structures drawn this way. I'll put R here for restive molecule. This is sometimes a double bond, sometimes a single bond. This is sometimes a double bond, sometimes a single bond. So this one solid line with dashed in this context represents 1.5 bonds. It's intermediate between a single and a double bond. Similarly, the negative charge is delocalized. Half the time the negative charge is here, half the time the negative charge is here. That's a delocalized charge. Whenever charge can be delocalized, that stabilizes the ion. So this is sometimes called a resonance stabilized anion. It is, in terms of a base, this is a weak base. Weak base. The hydroxide, you know, is a strong base. It has no resonance. No resonance to stabilize it. You can think the only way to stabilize this one is to grab a proton, then it becomes H2O, very stable. This is a strong base. So when we talk about bases, this is a weak base, whereas hydroxide is a strong base. I'll try to illustrate what that means. We're talking about the anion grabbing a proton, H+. Hydroxide has a negative charge. It's ready to grab an H+. Gulp. Got it. The carboxylate ion, like acetate, is not a strong base. It has a negative charge, but that negative charge can move. And for example, maybe this one's saying, I'm ready to grab an H+, but no, I'm not. I'm ready to grab an H+, but now I'm not. So since the negative moves, since the negative is delocalized, this is not as good a base as this hydroxide, which just has one negative charge saying, here, give me an H plus, I'll take it. So in a sense, for this one, if you might say, well, pick up the proton, pick up the proton. This one might say, not now, I'm resonating. I'm busy, I'm resonating. And if it does grab the proton, the game stops. The double bond can no longer move. The negative charge is covered up. Sad. I don't get to resonate anymore. Resonance makes a lower energy state, a more stable state, one that is more likely to stay in its deprotonated form. Resonance is satisfyingly modeled with orbitals. You may recall that this is a representation of a p orbital. When p orbitals line up on adjacent atoms, you can create a double bond. It's called a pi bond. But in the structures that you've seen, like the carboxylate ion, it's symmetric. This oxygen has a p orbital. This oxygen has a p orbital. The central carbon has a p orbital. Where's the double bond? Is it here? Is it here? In reality, it's in both places. It's symmetric. That's what the resonance model is all about. From above, it looks like this. And this is sometimes called a pi network made of p orbitals.